All right, let's get started. Are there any questions? Nothing? Okay. All right, so homework number one is going to be assigned. It'll probably pop up on Blackboard. I want to say around 1 o'clock, maybe 1:30, something like that. That'll be due in a week before class begins next time, right? Refer to the homework instructions guide if you have any questions, or you can ask me as well. All right, so we want to just wrap up transfer function stuff and then move on to block diagrams, which is our main thing for today. So let's say we have a transfer function y of s over u of s is equal to, let's just say t of s for now, right? And I want to solve for y as a function of time. How would you go about doing that? What's a step-by-step process here? So I want to solve for y of t. Inverse Laplace transform right away. So first we need to move the u of s over, right? And then we can do an inverse Laplace transform of this entire thing to get y as a function of time. It'll be the inverse Laplace transform of t of s times u of s, right? We cannot do the inverse Laplace transform of y of s over u of s is equal to the inverse Laplace transform of t of s. You're not going to get the right result there, right? Is this what I've written here? Is that the same thing as this? Yes? How many of you think yes? No. I don't know. Okay, I need more hands than that, guys. Come on, there's like 45 people in here and I got maybe 10 responses. Let's try again. Yes, these two are the same thing. Okay? No? So it's about 50-50 and I don't know. All right, at least you're proud about it. Okay, these are not the same thing, right? Laplace transforms and inverse Laplace transforms, you can split them up if it's addition and subtraction, right? But if you have two things that are a function of s, you cannot just split those pieces up and do the inverse Laplace transform separately, right? You will get the wrong answer. So these are not the same thing. Do not do that. That is the big thing that I want to cover here. Do not do this either, right? Those are the two things you don't want to do here, right? If you're solving for y as a function of time, move everything that's not y over to the other side and then solve for the inverse Laplace transform. Okay? Now, what if we have multiple inputs? So let's say I give you two transfer functions, T1 and T2. Same output for both of them. And I want to solve for y as a function of time with u1 and u2 both being non-zero. How would you guys approach this? Any ideas? Solve for u1 and so u1 and u2 are control inputs right now, which I'm going to say those are known to you. So we already know them. Okay, so solve for y of s, but which one? So y of s is equal to t1 of s times u1 of s, or is it y of s is t2 of s, u2 of s? These need to be the same thing. Yeah, but u1 and u2 are, I just said, are known, and t1 and t2 are known. They're not necessarily gonna end up being the same thing here. Right. I'm looking for the total response. Maybe that's a hint. I'm hearing a lot of whispers. You add them? Exactly, right? The total y of s would be t1 times u1 plus t2 u2. And then you go from there, right? This all has to do with the fact that these are obeying superposition, right? And that we have the system is linear, pretty much is where it's coming from, right? We're not going to deal with this too much until we get to what the equivalent of in the book is chapter 7, steady state responses with disturbances and control inputs. But this is something good to keep in mind here, right? So if we have multiple inputs, right? We can find a transfer function for each one separately, right? But then if we want a total response, the aggregate response, we need to combine them together. Okay? Any questions on that? All good? All right, so let's keep in mind why we're using transfer functions. Why transfer functions matter? What do you guys think? You guys have already seen them in a class or two, right? In Laplace transforms. What's the value in them? Find the roots, right? What are the value of the roots? So we haven't even covered that yet. Right, but that is relevant. That is a good answer. Finding the roots or the poles, as we'll talk about a little bit later, that relates to it. They describe system behavior in a generic fashion, right? Did I say this is a mechanical system? Did I say this is an electrical system? Did I say it's a thermal system, a fluid system, right? It doesn't matter. What we're going to be learning in this class is irrelevant for our system. And some people are here are saying stability that relates to the roots, makes it easy to analyze the system in the frequency domain. That's also good, right? But it's generalizable, right? The techniques that we're going to learn apply to motors, they apply to batteries, they apply to the temperature in these rooms, right? And how to control these different items, right? So it's generalizing things. And if we want to have things that are generalized, we should have a generic model that can apply to all these types of things. And that's our transfer function for this class. State space can also do that. All right, so that wraps up transfer functions. Let's get into block diagrams. I feel like I asked you guys this in the first class, but I forget. How many of you guys have done work with block diagrams in 3333? Hopefully all of you guys, right? If not, then you're probably going to need to spend some time reviewing it again because they will be relevant in this class. They're going to pop up a lot because they are relevant to control. So block diagrams, what are they? Block diagrams are a visual representation of a system using transfer functions. Typically. Right? If we're using transfer functions, what does that mean for our system? What is a word that we can use to describe our system if we are using transfer functions? The system is blank. Say again? Linear. Linear, right? Using transfer functions, the system is linear. Right? We can include initial conditions in block diagrams. We're going to leave that out for the most part. So we're going to typically in this class neglect initial conditions. Okay. So let's say we have a system. We're going to go over this in the next class, but your typical mass spring damper, which everyone should be able to get a model for this system, where our force is our input, right? And let's say our output is, I don't know, velocity of the system, something like that. We can get our transfer function, which we'll call T of S. We'll go through this in the future. But we can get a transfer function for this system, right? Where C, M, and K are parameters of our system, right? And we're trying to measure, let's say, velocity of that mass, let's say. All right. We can rewrite this as we just went over. Y of S is equal to T of S times U of S, right? So we can write it that way. What is the block diagram for this system? What would it be? Let's see how much you guys remember about this stuff. We're going to be drawing something. Any ideas? How many of you guys don't remember block diagrams at all? All right. Time to review it today, right? So I'll give you a hint. In the sense I just said, there's a hint as one element that's going to be in this. Block, right? There's going to be a block. It's a block diagram, right? So probably something like this, right? Maybe that's starting to look a little bit familiar, right? What do you think is going to go in that block? What was it? Input. Not quite. Input's going to be relevant. T of S. right? Transfer function's going to go in there. I could have written out the full thing, right? Transfer function's going in, or the transfer function is in the block. The input goes into the block, and the output comes out of that block. Y is equal to T times U, right? That's what a very simplistic block diagram would look like, right? So we can see there is an arrow. Arrows are associated with signals, right? Inputs and outputs typically, or something relating to those, right? So inputs are not going to be in blocks almost always, right? Inputs are going to be associated with our arrows. Those are signals. Same thing with outputs, right? If an arrow, a signal, right, goes into a block, the signal is what? It's multiplied by what's in that block, right? Right? And that produces a new signal. We get a new signal coming out of the block. Right? That new signal coming out of the block, it's U times T, which we already defined as that's Y. All right. So there are 4 core pieces to a block diagram. 4 elements that are going to make it up. All right. The first one, the arrow, I guess I should draw it out. So number 1 is our arrow. The arrow carries a signal, right? U, Y, or maybe some other letter, right? Something that's usually going to be a function of time is associated with our signals here, right? Then we have our blocks. The block, which represents a transfer function. In a sense, the blocks represent our system dynamics, right? Those are the 2 pieces above. Our third piece, anybody remember what another thing that would exist with block diagrams are? The circle, right? Or our summer, right? So I usually put the symbols in here, but you can also put them associated with the arrows themselves. It depends on how much space you have, right? The summer or the circle, it adds and or subtracts things. Right? The block is like a multiplier, right? Usually with a transfer function in there, right? A summer circle adds or subtracts things. What about the last piece? Probably the one that comes off as maybe the most confusing at times for people. Anybody remember? Feedback loop. A takeoff point is usually what it's called itself. The feedback loop is when you use a takeoff point to connect something in behind it, right? So the takeoff point branches the signal to use at other parts in the diagram. It is not splitting the signal in half, it's cloning it. Right? It's duplicating it. That's what a takeoff point does. All right. So we'll go through some pretty basic examples here and talk about how to take in an equation or a transfer function, turn it into a block diagram. And then if we have a block diagram, how to figure out what our transfer function or our system dynamics would look like from it, right? So the easiest example, let's start with multiplication. So y of s over u of s is equal to 3, right? And I want to get a block diagram for this system. So preferably from someone that hasn't participated yet. How do we get a block diagram for this? The 3 would be inside the block, right? So I'm going to take one more step before that, right? I'm going to say y of s is equal to 3 u of s, right? I'm going to rewrite it out so that we don't have one signal divided by another, because those don't tend to show up in block diagrams. Then absolutely correct, right? The 3 would be in the block. Why not the u? It's a signal, right? Something that's kind of like time dependent, right? So our u is going to come in, and then what's coming out of this block? 3 times u, which is y, right? Nice and easy. Okay, let's ramp up the difficulty just a little bit. Let's do integration. All right, so let's say we have x dot is equal to u, y is equal to x. So u is our control input, it's a function with respect to time, y is our output, and I want a block diagram from u to y. First of all, why did I call this integration? If that's the case, I don't see an integrator in here, I see a derivative. So how would you do that? We can do the Laplace transform. That's what we're going to end up with, right? But even simpler than that, you can go back to like calculus 1, right? And you could just solve this, right? So we can solve for x as a function of time here, right? What's the solution to x as a function of time? So we have dx over dt is equal to u. U is a function of time. What's that going to be? Dx is equal to u dt, and then you integrate over the ranges, right? And you end up with x is equal to x initial, which we're, like we said, we're going to kind of ignore that for most part in these block diagrams at least. And then we're going to integrate u with respect to time, right? From 0 to t, right? Then what is y? The same exact thing. Y, which is equal to x. It's integration of our input, right? And that's why this is called an integration problem, right? So how can we get a block diagram for this? Right? This is not multiplication or addition. This is a integrator, right? Block diagrams don't do integration, right? They do addition, multiplication, subtraction. That's it, right? So how do we do that? Laplace transform, right? So let's do this again in the Laplace domain. Laplace transform of x dot is equal to u. What is that going to be? S times what? X of s, I heard, right? Minus that initial condition, right? Which we're going to say is 0, is equal to u of s, right? We can solve this for x of s. That's 1 over s times u. All right, we can see the relationship. The derivative of a signal, right, is represented by s being multiplied by that signal, right? Integration is 1 over s, right? It's an easy way to keep track of that sort of stuff, right? Integration is 1 over s times a signal. And then we have a Laplace transform of y is equal to x, right? Or y of s is equal to x of s, which is 1 over s times u. So now, what's our block diagram going to look like? U times 1 over s, but how do we represent that in our block diagram? So we have an arrow. What's on the arrow? U of s. And then what do we have next? A block with 1 over s, a very basic transfer function. And then what's coming out of this? y of s, right? Or x of s, right? Depending on the context that you're going for here, right? But this is how integration is going to be represented in a block diagram. Okay? A general transfer function we already went through. I'll just write it down quickly one more time. It's the same as multiplication. Right? If we have y over u is equal to t, we can just solve for y. And then write this out as our block diagram. U goes in, t is in the block, then t times u, which is y, is going out in this case. Pretty straightforward. Okay, so multiplication and transfer functions, they behave the same way. Integration is a form of multiplication, right? Same things with derivatives, because those are just s and 1 over s, or 1 over s and s respectively in our Laplace transforms. Okay, what about addition and subtraction? All right, so let's say y, again, a function of time, is -8, u1, also a function of time, minus 9u2 plus 7u3, right? And I want to get a block diagram for this system. So what do we do in this case? Is it going to be nice and simple like all these multiplication examples here? Probably not, right? So how do we do this? So first thing, Laplace transform is what I recommend, right? So Laplace transform of this. All right, just for our class, we're going to focus on when we do Laplace transform. We're working with transfer functions, okay? What do we do from here now? We have a lot of different options for how we approach this. So what do you guys think? What's your instinct? Circle, okay, I'm going to draw a circle. What else we got? You participated enough. Let's give somebody else a chance. Oh, I saw you raise your hand actually, so. Okay, so let's stop there, right? How about for every input, let's assign it to an arrow. Okay. Wait, so hold on. You're saying let's go one step at a time. So now these go into boxes, right? Or blocks. Okay, and somebody else, what's going into these 3 blocks here? Maybe someone online, let's go with, since we do have a decent number of people there now. What goes in the first block, second block, third block? Coefficients, yes, but how do you want to choose your coefficients? I see -8, -9, and 7. Okay. All right. What do we do from here? So what's coming out of this block here? Right. So this is -8 u1 of s. All right. This one is going to be -9 u2 of s. And this is 7 u3 of s. Right. Okay. What do we do with these guys? All right. So put them into the circle. I'm going to be sloppy in how I do it. Okay. What else? Say again? Positive signs for which ones? For all of them? Okay. Now what? We have an arrow coming out of this, right? And what does that arrow have? Well, it's -8 U1 of S minus 9 U2 of S plus 7 U3 of S, which is in this case Y of S, right? How many outputs can a summer have? A circle. Only one, right? You can have as many going in as you want, but you can only have one coming out of our summers. Keep that in mind, right? What about blocks? How many things can go in and how many things can go out of a block? Just one and one, right? A block only has one thing going in and one thing going out here, right? Okay. So this example covers addition, but I want to do addition and subtraction. We'll get to this in 1 second. All right. So there's no subtraction here. This isn't the example I wanted. Is there a different representation we could have had for this system to get the same thing? Hold on. Are you guys answering or? Okay. Yeah, I think you were first. Okay. If 8, right? And then this is 8. And then what would this be? Right? And we could do that for any of these signals. We could have even done it for this one. We could put a -7 here and then a subtraction up here, right? There are, I don't know if technically, I guess technically if you want to play with extra blocks and stuff like that, an infinite number of combinations that you could have to represent the same thing with different block diagrams, right? Okay, we had some questions.
That was my question.
Yeah, so it's up to you how you want to represent it. Sometimes things are going to make me or sometimes it's going to be up to you how you want to decide it. It really is going to depend on the situation. You're going to have to make judgment calls here. Could you give a physical example of a system that would have multiple inputs like shown in this block diagram? Let's go back to class number 1 here, right? So class number 1, we were talking about a car, right? How many inputs could a car have? A lot, right? We went through a bunch of different examples. The major ones being our accelerator, our brake pedal, right? Even if we mash those together, right? We could also have steering if we want to argue that as well. We could also have, if we were just looking at like a 1-degree body system, just lateral motion. We could also include things like wind velocity or things like that, right? Like the gusts that are fighting against our system. There are plenty of multiple inputs that we would have for different types of systems, right? An airplane is not built off of just pressing one button, right? It's a bunch of different things, right? Any other questions? Okay. Does a split signal thing not count as 2 outputs? I think we're going to get there in a second, right? But we could have multiple outputs if we want to for a system, if we're measuring multiple things. But a takeoff point is what it sounds like you're describing there. A takeoff point is just cloning a signal, right? And it doesn't have to be with just the output. I could have a takeoff point with this U3 here if I wanted to, right? Or I could have a takeoff point with this point. Is there a question over there? No? Right? It's cloning a signal, right? So it's not changing how many outputs we have. It's just taking that signal, maybe we're going to use it somewhere else. All right, another example here. Y is equal to 5y plus 10u, right? And we can do our Laplace transform. Y of s is equal to 5y of s plus 10u of s, right? There are, let's say, in this case, 2 major representations that we can have for our block diagrams here. All right. What are the 2 ways that we could represent this system? Just go with one. It's easier if you're the first one to go, right? Block. Okay, what's going in the block? Okay. Anybody else want to help out? What? 2 in the block? Where's the 2 coming from? Yeah. I don't see a 2 anywhere here. Oh, you participated again a lot, so let's let other people get a shot. Somebody over here. Okay, too many. Let's do hands. It's just too hard to control here. So I think you had your hand up first. Yeah. 10, right? So what's coming out of this? 10 U of S. Somebody else? Another block? So I don't think another block at this point, unless you're going to put a 1 in there, right? Because we've already gotten this, right? Summer, okay. All right, I think somebody else said a circle as well there, right? Okay, what's going into this circle? We want to match this equation here. Probably a plus right here, right? And then do we have something else that we maybe want to add to this summer? What do we want to come out of this summer? Let's put it that way. Probably Y of S, right? So how can we make that happen? Oh. Yes, that's where we're going to go here. I'm going to work backwards from it, right? So we probably want something else going in here. What does this signal need to be? Can you say it louder? Takeoff point, we're going to get there. I'm working backwards. I'm working backwards from here to the takeoff point. So what does this signal just on its own need to be? If this is Y, this is 10U. Just 5. I heard 5. Is that right? 5 Y of S, right? Right, -4. We'll get to that one in a second, right? And this needs to be a plus here as well, right? Now we have written this side of the equation, right? We just need to figure out, we can't just have a Y of S floating out here, right? Because it already exists somewhere else. And this is where the takeoff point comes into play. We clone this Y of S and bring it back, and we have some sort of feedback loop here, right? This is one way to represent your system. This one doesn't require having to solve any equations or anything like that, right? You are looking at the equation as is, right? And just writing it out step by step. You see this term here, so you need to have a 10U somewhere, you need to have a 5Y somewhere, and it needs to be equal when you add those two together to Y itself, right? That's one way to represent the system. I think we do need a box there. Thank you for catching that. There we go, because this is Y, right? It's cloned, and then we need to multiply it by 5 to get 5Y of S. Good catch. Other questions? All right, what's the other way that we can represent this? Somebody online is already kind of getting towards that sort of. So yeah, I think that's what somebody had online, right? So we move -5Y of S, we move it over to the left side, we get -4Y of S is equal to 10U of S. Right? And we probably don't want to represent it this way because we want to have a Y somewhere in our system, right? So what would you do from here? You can answer this time. You're good. What was it? Divide by -4, right? Solve for Y, right? So that's your other option, is you could take all your equations, right? They're going to be algebraic, and just solve for Y straight out as a function of U. All right, we will be doing both forms of this in the future, right? Essentially, it's going to be open loop transfer function versus closed loop transfer function, right? So an alternative is U of S -2.5 Y of S. Right? This one seems a lot more simplistic, right? But it requires a lot more upfront work, right? We need to solve for Y, right? It's easy in this case because we're only dealing with U and Y in one addition thing. But if we have a whole bunch of different variables that are existing, or a whole bunch of different equations, like you guys will see in the homeworks, right? this may be a lot of extra work when you can just write out the equations as is. Okay? How much time we got here? We got like 15 minutes. Okay, so let's do at least one more example here. I think we got a couple actually. Let's see. Yeah, let's go the other direction here for at least one example. And let's get y of s from a provided block diagram. This will be a pretty important skill moving down the road here. So we have u1 is multiplied some sort of constant alpha. And then that is going into a transfer function b1 over s plus a1. That's going into a summer that's eventually going to produce y for us. But we have a second input, u2, which is going to be going into beta, another transfer function. We'll keep it first order. And that's subtracted from the other one. All right. And what we want to do is get y of s, right? Or potentially, if we only had one input, y over u here. All right. So there's a handful of different ways to do this, right? I bet a lot of you can just kind of like go through this very quickly. What I like to do, this one's fairly simple, but what I like to do sometimes is just label every signal in the system. I would call this A of S. I'd call this B of S. I'd call this C of S. I'd call this D of S. And I'd solve for those ones individually. That's one way to go about doing it, right? Maybe useful for one of the homeworks coming up, right? And then solving for what of A of S is, right? So what is A of S in this case? Right. So in this case, we probably don't need to label them. We could just say, we know this is alpha u1 of s. Then what's B of s going to be? Alpha times this transfer function, right? Times u1 of s. Right? It's pretty straightforward in a diagram like this where everything's flowing from left to right. We have a takeoff point. If we have a feedback loop at all, maybe it gets a little bit more complicated, right? Same thing for the bottom, right? We follow u2. So in some cases, it depends on the situation. Sometimes you want to start at the output and work your way backwards, right? In this case, you want to probably start with your inputs and work your way forwards, right? So for this one, I'm going to follow u2. It's going to flow through this beta block. So I get beta u2 of s, right? Beta u2 of s flows through this transfer function block. So I end up with beta b2 over s plus a2 times u2, right? Now I have both of these things that are going in together. Y of s is what? It's just the two of these things, or the second one subtracted from the first one. So it's alpha b1 over s plus a1, u1 of s minus beta b2 s plus a2 u2 of s. Right? Pretty straightforward in this case. Examples we'll do in the homework are going to be a little bit more complicated than this. It's going to require you to think about how you deal with takeoff points. Any questions on that? All right. What we can also see from here is that we've actually identified the transfer functions, right? This could be called T1 of S, right? This could be called T2 of S, right? And so we could get Y of S over U1 of S. That's T1 of S. That's alpha B1 over S plus A1, right? And Y of S over U2 of S. That's T2. That's negative beta B2 over S plus A2, right? Times U, no, because we moved the U2 over, right? So we can get our transfer functions from our block diagrams if those are provided to us already. All right, let's just do a few like quick summaries for different rules that we have for block diagrams. So we can combine or manipulate the form of a block diagram. I'm going to focus on one input and one output cases for these. All right. So one example, if I want to simplify the following, we have U of S going into T1 of S. That goes into T2 of S. That goes into T3 of S. And then we're spitting out Y of S. What is a faster way to represent this? From U to Y. Right? We can look through this, right? And go through the math this first time just to be a little bit safe, right? What is this signal right here going to be? T1 of S times what? Times U of S, right? What about this guy? T1 times T2 times U, right? What about this one then? We can kind of see the pattern here. And that's what Y is, right? So if we have things where we're not having any takeoff points in the middle that we may need to use, right? And there's no summers or anything like that. If you just have multiple multiplications in a row, right? You can just combine them all together. This is just T1 times T2 times T3, right? That's one rule that may be useful for us moving forward for our block diagrams. If we have multiple things that are just multiplying in a row, straight across, right? Just blocks and signals, we can just combine them all together into one big box. What about a case where we have, let's say, a summer with, I'll do 3 pieces here. So we'll start with U of S, but we're going to have 3 transfer functions. So let's call this T1 of S, T2 of S, and T3 of S, right? And U of S is going into all of them. So we're going to clone it, and it goes into all of these, and then the outputs of these guys go over here, and that's how we get Y. And it doesn't even need to be Y. It could just be another variable, right, that we're trying to combine. Right? What's a simpler way to break this down? Simplify our representation for this particular case. Any ideas? If you don't have an idea, go through what we just did in the last couple of examples, right? Assign a signal to each one and solve for Y. Right? So we have U of S going in, right? And it's multiplied by T1. It's also multiplied by T2. It's also multiplied by T3. And those are all adding together, right? We can just group them that way. Just like we normally do when adding things. And that's going to be Y of S. All right, pretty straightforward. Okay, let's hit on the block diagram that we are going to use the most in this class. So get familiar with this and get familiar with it now. Question? So which, this one or the one before this? Mm-hmm. Mm-hmm. So U of S doesn't go in a box. Is that what you're saying? But I'm saying that you should never put U of S in a block itself, right? That's something that we need to keep in mind, right? U is a signal, Y is a signal. Those do not go in blocks, right? Because they're time varying, right? So we're not going to ever put U or Y or anything like that in a box or a block, right? The blocks are reserved for multipliers, and transfer functions. That's the only thing that goes into them. Okay, let's make sure we keep that in mind. All right, so the most common thing we'll be using here, feedback form. How many of you guys have seen or heard of feedback form? I think I drew it a little bit first class, so really everyone should be raising their hands. Right? Feedback form. Remember in the first class, I said we have control inputs, we have exogenous inputs or disturbances, right? And then I think I very briefly mentioned that we could have a third type of input in this class that we're going to use a lot. I'm going to call that a reference input. Right? We'll get into the details of that a little bit later on, but the standard feedback form says that we have a summer, the reference value is coming in, it's added in, and we're going to have something subtracted from it. That is going to go into a block. For now, I'm just going to have that block as G of S, right, for a generic plant transfer function, right, our system itself. And then this is going to be output as, well, the book uses C here. I am going to use Y of S instead for what comes out of this, right? Yeah, well, we'll go with that for now, right? This actually isn't going to be G. We're going to use a different letter for this in the future. I'm going to just call it Q for now. All right, we're going to feed this back over here. All right, so this is still Y of S. This is H. So this signal is going to get multiplied by H and fed back in. This is a negative feedback loop here. Right? What is, if we want to write this out as just our reference, what we want Y to be, then we just want one big block here and get Y out of it. What goes in that big block? Right? Q of S minus what? Q of S minus H of S? That seems way too simple, right? So let's not take guesses here. Let's go through this step by step, right? So what I recommend is you label every one of your signals that don't have a label. Do you have a question? So let's, yeah. Yeah, we're going to go through that proof, but I think you got it. Yeah. I think there should be a 1 somewhere in there, right? Got a 1 plus something? Okay, we'll double check it, right? So I'm going to call this signal here E of S. I'm going to give a name to it, right? What should I call this signal here? What is this one? H times Y, right? We have H multiplied by Y. This is H of S, Y of S, right? So then what does E of S end up being? Exactly, right? So then what does Y of S equal if we have that signal going through that Q, right? Y of S is going to be Q times E, right? And what's E? R minus H times Y, right? And now we can solve this for Y. So what do we end up with? We're just going to distribute out that Q. Oops, it's Y of S over there. All right. Tell me what Y is. Well, we're running out of time here. So I think we got to wrap it up here, unfortunately. I will put the solution to this online at some point. But what you guys should do, in addition to the homework, right, get some practice in. Again, most common block diagram we're going to be dealing with here. Make sure you can figure out what this is on your own. I will put the solution up later as well as a couple of other examples. All right, don't forget about the homework. 1 week to do it. Have a good weekend.